Section 12.5, the normal distribution. And here we have four objectives: to distinguish between discrete and continuous random variables, to apply the properties of a normal curve, to convert between z-scores and normal curve score areas, and interpret normal curve and areas in several ways. As you will see, the idea of a normal distribution is extremely important in inferential statistics and in statistics in general. So we will have a lot of details to discuss. So when it comes to inferential statistics, it treats data distributions according to the nature of the random variable involved. And so let's talk at the two kinds of random variables that are typically discussed. And the first one is the discrete random variable. And we've talked about this one before. It can take on only certain fixed values. For example, the number of heads in the 5 tosses of a fair coin may only be one of the following numbers: 0, 1, 2, 3, 4, or 5. That's it. And on the other hand, a continuous random variable can take on all real values over a certain range. And for example, the diameter of a mature camellia blossoms can be any real number in the range, let's say, between 5 and 25 centimeters. Or the number of gallons of milk a cow can give, that's a continuous random variable, because it can change, from one day to the next for sure, and even the actual amount. So that's another example of a continuous random variable. Now, it turns out that most random variables discussed earlier in this chapter were empirical, or based on experience or observation. Now, the distributions covered in this section are theoretical, based on theoretical probabilities. And there's a reason for this, because a knowledge of theoretical distributions enables us to identify when actual observations are inconsistent with stated assumptions. So you may want to read that sentence again. A knowledge of the theoretical distribution enables us to identify when actual observations are inconsistent with stated assumptions. In other words, it can be used as a check. So here's the probability distribution of the number of heads for 5 coin tosses: 0 heads, 1 head, 2 heads, etc., all the way to 5 heads, and the corresponding probabilities. We can graph this very nicely. Here's the number of heads: 0, 1, 2, 3, 4, 5, and on the vertical axis is the probability, or relative frequency, of the number of heads. The next probability distribution is for camellia blossom diameters that cannot be tabulated or graphed in the same way, because the variable itself, the diameter, is continuous. We could say the graph would be smeared out into a continuous bell-shaped curve rather than a set of rectangles as in the previous example, as shown in figure 13 here. The vertical scale on the graph in this case shows what we call probability density, the probability per unit along the horizontal axis. So this is an important figure to keep in mind, the distribution here bell-shaped, and this would be the probability density. And we'll be discussing this in more detail. Because normal curves are so important in statistics, let's talk about the definition and properties of a normal curve. So again, the camellia blossom curve is highest at a diameter value of 15 centimeters at center point, and then drops off rapidly and equally toward a 0 level in both directions. Such a symmetric bell-shaped curve is called a normal curve. Any random variable whose graph has this characteristic shape is said to have a normal distribution. So that's where normal distribution will be used frequently here in the near future. Next are some very important observations about the normal curve. Number one, the area under the curve along a certain interval is numerically equal to the probability that the random variable will have a value in the corresponding interval. Okay? The area of the shaded region in figure 13, showed previously, is equal to the probability of a randomly chosen blossom having a diameter in the interval from the left extreme, let's say from 60.4 to the right extreme to 21.2 centimeters. Normal curves are very important to the study of statistics. And the reason why they're so important is because a great many continuous random variables have normal distributions, and many discrete variables are distributed approximately normally. So even when random variables are discrete, in many cases we can assume they're distributed normally. So each point on the horizontal scale of a normal curve lies some number of standard deviations from the mean, positive to the right, negative to the left. And the number of standard deviations for that point, number is the standard score. We already discussed that because that's the same as a z-score that we computed earlier. You may remember that there are many z-scores you were asked to compute. That's how many standard deviations the data point is above or below the mean. Well, we're coming back to that point here again. Okay, here are some of the normal curves and what they can look like. And for example, the curve, curve S in red is a standard curve with a mean of 0. Here's the mean, and a standard deviation of 1. So that's the red curve here. Then curve A has a mean less than 0. It's shifted to the left, but has a standard deviation also equal to 1. Then curve B, the blue one, has a mean of 0. It's centered at 0, as you can see, and a standard deviation of less than 1. In other words, it is narrower than the red one. The red one has a standard deviation of 1, and the blue one has a standard deviation less than 1. Or the green one, rather. And then when you look at curve C, again, that has a mean greater than 0. It's shifted to the right because the center is about here. And it's flatter, so it has a standard deviation greater than 1. So curve B has a standard deviation less than 1. It's narrower. And curve B is much flatter, so it has a standard deviation greater than 1. So that's just to have some kind of feel what normal curves look like and how the standard deviation figures into this. In other words, the standard deviation makes the curve narrower when the standard deviation is less than 1, and it makes it wider or more spread out when the standard deviation is greater than 1. Next, we'll discuss some very basic but very important properties of normal curves. Number one, we already mentioned that the graph of a normal curve is bell-shaped and symmetric about a vertical line through its center. The mean, median, and mode of a normal curve are all equal and occur at the center of the distribution. In other words, this line here is equal to mean, median, and mode. Then there's the empirical rule, and that comes up quite often. The percentages of data values when given distances of the mean in both directions are approximately as follows. 68% of the data are within one standard deviation. Again, one standard deviation to the right and one standard deviation to the left. Okay, so that's all something you have to remember. And it's 95% within two standard deviations to the right and two standard deviations to the left. And you have over 99%, 99.7%, within 3 standard deviations to the right and to the left. So 3 standard deviations over here, and then to the left 3 standard deviations over here. So most of the data, you can say, is within 3 standard deviations of the mean. Obviously, there could be something out there, and that would be certainly okay, but most of the data, 99.7, is within 3 standard deviations of the mean. Okay, let's apply the empirical rule. Suppose that 300 pre-medical students take a midterm exam, and the distribution of their scores can be treated as normal. Find the number of scores falling into each of the following intervals within 1 standard deviation of the mean for the A part, and part B within 2 standard deviations of the mean. Well, up here we just learned that 68% of the distribution is within 1 standard deviation. And so that's what the question is here. In other words, 68% is 0.68, and 0.68 of 300 is equal to 204. In other words, 204 of the exam scores would probably fall within 1 standard deviation of the mean. Similarly, within 2 standard deviations of the mean, we know that 95%, about approximately 95% of the data is within 2 standard deviations of the mean, and 95% is 0.95, and 0.95 times 300 is about 285. So we would expect 285 out of 300 exams be within 2 standard deviations of the mean. So to expand on this a little bit, on these results here, these of course are the theoretical numbers, empirical rule, but they can help us see if the actual results are reasonable. For example, if in the actual exam it turns out that only, let's say, 150 of the exams are within 1 standard deviation, then there would be a reason to investigate that and find out why. It would be very non-typical. So in other words, this gives us a number to expect. What should it be? It probably wouldn't be exactly 204, but it would be around 204 or thereabouts. Probably not 150. Again, that would be a very unusual result if that's really what happened. So here's a calculation that can help us discern whether the expected value is close to what it should be, what the result should be. Table 16 is the very typical areas under the standard normal curve, and here's an explanation. In the column under A gives the fraction of the area under the entire curve that is between z equals 0 and a positive value of z. And because the curve is symmetric about the 0 value, the area between z equals 0 and a negative value of z can be found by using the corresponding positive value of z. So in other words, if we have a negative z value here, we simply use a positive one, it'll give us the same area. For example, a z-score of 0.57 means the area under the curve is 0.216. That's what this means. Or a z-score of 1.70, which gives us an area of 0.455. So let's apply the normal curve table. And so use table 16 to find the percent of all scores that lie between the mean and the following values. 1 standard deviation above the mean and 2.45 standard deviations below the mean. So we're looking for a z-score of 1 and the associated area or percentage. So z equals 1, so we go into the table here, and we look for a z-score of 1, and it's right here. And it says 0.343, so the associated probability is 0.343. And since we are supposed to state it in percent, that means 34.3%. Similarly, the question, what percent of all scores lie between the mean and 2.45 standard deviations below the mean? Well, we go to 2.45, and 2.45 is the value here, 0.493. 0.493. 2.45 standard deviations, so 0.493, so 0.493. In percent, of course, it would be 49.3%. And because the curve is symmetric, we don't have to worry about a negative z-score, because obviously it is negative when it's below the mean. But in terms of area is not negative. So that would be the percent of all the scores that are 2.45 standard deviations below the mean. Let's look at example number 3, finding probabilities of phone call durations. The time lengths of phone calls placed through a certain company are distributed normally with a mean of 6 minutes and standard deviation of 2 minutes. If one call is randomly selected from phone company records, what is the probability that it will have lasted more than 10 minutes? So one way to start is to draw a distribution, a normal distribution. Again, it doesn't have to be to scale, but just something that will make sense. So there would be the distribution, and so the mean is 6 minutes, and the standard deviation S, so the x bar is equal to 6 minutes, so this is in minutes, and the standard deviation S is equal to 2 minutes. And so the question is, for 10 minutes phone call, if it's greater than 10 minutes, we're looking for this area here. Of course, this is the mean. Now, so the question is, what's the z-score? How many standard deviations are we above the mean? Well, we can just calculate it if you wanted to. Find the z-score for 10 based on a mean of 6. So z is equal to 10 minus 6 divided by the standard deviation of 2. So that's 4 divided by 2, or 2 standard deviations. Okay, so 10 is 2 standard deviations, which makes total sense because it would be 8, and that's 1 standard deviation, another one, so 2 standard deviations. So now we're looking for a z-score of 2, and when we look that up in the table, the area is 0.477. In other words, this area here is equal to 0.477. Okay? If you look on table 16, look for a z-score of 2, and you would find 0.477. Now, the way it's going to help us is that we know that half the area under the curve is on the right side, half the area is on the left side. So in other words, on the right side, we want to know this little tail here. So we find that out by subtracting this from half the area. 0.5 minus 0.477. half the area minus this area will give us the remainder here. So in other words, there's 0.023. So that's the probability that a phone call will last more than 10 minutes. In percent, of course, it would be 2.3%. Again, to determine the area here, we subtract the area we just computed based on a z-score of 2. The area based on a z-score of 2 is 0.477. That is this area here. The whole half area is 0.5. So we subtract from 0.5 this area here. We get the tail end here, and that's equal to 0.023 or 2.3%. In the next example, we are asked to find areas under the normal curve, and the one on the left says find the total area that is shaded in each of these figures. So here's a z-score of minus 1.45. So z equals minus 1.45. So we look at the table number 16. We look for a z-score of 1.45. And that is the corresponding area is 0.426. 0.426. So the area is equal to 0.426. And then for the z-score of 2.71, again we look for a z-score of 2.71, and we find that to be 0.497. 2.71, area is 0.497. So A equals 0.497. So we add these areas to get the total area. So then the total area is equal to 329, so 0.923. So that's the total shaded area. The next question asked us what's the shaded area between these two z-score values. Well, so here we look at the area for the z-score of 1.59. Z equals 1.59. And the corresponding area, so 1.59. That is equal to 0.444. So 1.59, the z-score is equal to the area 0.444. And then the z-score for 0.62, the z-score for 0.62 is equal to 0.232. So 0.232, and that was for a z-score of 0.62. Now remember that the area 0.444 is from the center all the way to this point here. So, and the area corresponding to a z-score 0.62 is 0.232. That is this little area here. So in other words, when we subtract the little area from the big area here, then we get the area in between. So then the area, when we subtract these areas, then we get the area as 2.12. 0.212 is the area between the two lines. Based on what we've learned so far, we've now learned that for the standard normal curve, the following three quantities are equivalent, so they mean the same. Percentage, in other words, of total items that lie in an interval, or the probability of a randomly chosen item lying in an interval, or the area under the normal curve along an interval. So all these three things mean exactly the same: the percentage, the probability, or the area. So let's apply this to an example here. Let's say in one area, the distribution of monthly miles driven by motorists has a mean of 1,200 miles and a standard deviation of 150 miles. Assume that the number of miles is closely approximated by a normal curve, and find the percent of all motorists driving the following distances: between 1,216 miles per month and between 1,000 and 1,500 miles per month. A good way to start this particular exercise is to graph a distribution. And since we're told it's approximately normally distributed, so we graph a normal distribution. And we are told that the mean is at 1,600. So the mean is 1,600. And the standard deviation is 150 miles. So these are miles driven. And so now the question is between 1,200 and 1,600 miles per month. Well, 1,200 miles is here for the mean, so it will be 1,200 miles. And then 1,600 would be about here. So what we need to know is what this area is. What's the probability? What's the area? So we compute the z-score for this data value of 1,600. So then the z-score would be 1,600 minus 1,200 divided by the standard deviation of 150. So there would be 400 divided by 150. And that's about 2.67. So now we look at our table. What's the corresponding area for a z-score of 2.67? So 2.67, the corresponding z-score is 0.496. So 267, the z-score, the area is 0.496. So the area is equal to 0.496, which means that about 49.6% of all drivers are between 1,200 and 1,600 miles per month. So about half. The B part asks what percentage, given the mean of 1,200 miles and standard deviation of 150 miles, what percentage drives between 1,000 and 1,500 miles per month? So we do it similarly. We draw a normal distribution. The mean of 1,200. And then we ask between 1,000, so 1,000 is about here, and 1,500 would be about here. So in other words, we are asking, what is this area here? So we need to know the z-score for this point here and for that point. So for the 1,500, we have the z-score equals 1,500 minus 1,200 divided by 150. So there would be 300 divided by 150, and that's equal to 2. And for the other data value of 1000, the z-score is equal to 1000 minus 1200 divided by 150. So that's minus 200 divided by 150. And that's about minus 1.33. So now we need to look up the different areas. And the area corresponding to a z-score of 2 that would be equal to 0.477. So the area corresponding to 2 is 0.477. And the area corresponding to a z-score of minus 1.33. Remember, it's symmetric about the mean, so we look for 1.33. And we find that the area corresponding to a z-score of 1.33 is 0.408. So the area corresponding to this is 0.408. I'm running out of room here, so let me just rewrite this here. So the area corresponding to a z-score of 2 was 0.477. The z equals 2. And when we have a z-score of minus 1.33, the area was equal to 0.408. So we can add these two numbers to get the total area. So when we add 0.477 and 0.408, we had 0.885 or 88.5% of drivers drive between 1,000 and 1,500 miles. Again, this is miles here. So there would be 88.5%. In example 6, we are asked to identify a data value within a normal distribution. How do we do that? Well, we are given that a particular normal distribution has a mean of x bar equals 81.7 and a standard deviation of 5.21. What data value from the distribution would correspond to a z-score of minus 1.35? Well, we know that the z-score is equal to the data value, x minus x bar, divided by the standard deviation. So we are looking for x because we know what z is, we know what x bar is, we know what s is. So let's use the numbers. Z equals minus 1.35, so minus 1.35 equals x minus the mean of 81.7, and the standard deviation was 5.21. So we solve this equation by multiplying both sides by the denominator of 5.21. So 5.21 times minus 1.35 equals x minus 81.7. So then x would be 81.7 plus 5.21 times minus 1.35, and that is equal to 74.666, or we can round it up to 74.7 rather. 74.7. So that data value corresponds to a z-score of minus 1.35, given a mean of 81.7 and a standard deviation of 5.21. So remember, we just get started with the basic z-score equation or formula, and then we simply substitute for the z-score the given number, for the mean and the standard deviation, and then just solve this equation for x, and I'm sure you all know how to do that. In example 7, we are finding z-values for given areas under the normal curve. So the first part is assuming a normal distribution, find the z-value meeting each condition. 30% of the total area to the right of z. Again, a good way to start is with a normal distribution. So here's a midpoint, a mean. And so we are asked to find the area 30% to the right of the z-score. So we're looking for this particular z-score for an area that's 30% to the right. Now we know that half the area to the right is 50%, so that means that this area must be 20%. So we are looking for a z-score of with an area of 20. So when we look at the table, 16, what area is 0.20 or 0.2, 20%? Well, there's no exact value, but we have 0.198 and 0.202. So the 200.2 is right in between, 20%. So it'd be between 52 and 53. And so then the z-score would be the mean of the two values of 52 and 53. So 52 plus 53 divided by 2, or 52, 0.525. 0.525. So that would be the z-score corresponding to this area here. 20%. So z-score is 0.525. The second part asks us to find 80% of the total area to the left of z. So again, we begin with the distribution, normal distribution. So here's 0. We know 50% is on this side, and 50% is on that side. So that means we are looking for the area that is 30% on the right side. So 30% or 0.3. So we need to find the z-score for this area here, 0.3. So when we look at the area of 0.3, 30%, we find that that corresponds to a z-score of 0.84. So the corresponding z-score would be 0.84. So z equals 0.84. And so then that means everything to the left is equal to 80%. So one takeaway from all this is that for most of these exercises, you want to begin with a normal curve and write in the data that you have and think about what you need to do to calculate, whatever it is, a z-score or an area. Without it, it's much more difficult to do all this mentally and keep the numbers in your mind where they are and all of that. So begin with a little distribution and then fill in the data that you have. Let's talk about IQ scores and distribution of them. On standard IQ tests, the mean is 100 with a standard deviation of 15. With the results come very close to fitting a normal curve. Suppose an IQ test is given to a very large group of people. Use the empirical rule to find the percentage of people whose IQ scores fall into each category. So number 15 is more than 100. Well, let's draw a distribution of the normal distribution. So we are told that the median is 100, the mean. So, and we asked more than 100, in other words, to the right of 100. Well, we know that 50% is on the left side, 50% is on the right side. Therefore, 50% is to the right. And less than 85. Okay, again, let's draw a distribution. And so, again, here's 100 for the mean. And then 85. So that would be 15. There would be one standard deviation to the left. And we know that 68% are between one standard deviation. So therefore, we know that, so if this is half, then from here to the left is 50%, and this is 34%, because 34% of both sides is 68%, so then 50 minus 34 is equal to 16. So this area here would be 16%. So that's 15, that's 16. And let's look at number 17. Again, we're going to draw a little normal distribution here. There's 100 at the center, between 70 and 130. So 70, there would be 2 standard deviations to the left, because each standard deviation is 15, so 70 from 100 would be 2 standard deviations, and same with 130, that's 30 above or 2 standard deviations to the right. And we know that 95% of all the data between 2 standard deviations to the left and to the right is in this area here, so that's 95%. That's for number 17. So here the answer is 95%. And the last one would be for 115. Again, we draw a normal distribution. Send it at 100. And then 115 would be here, 115. And it would be 1 standard deviation to the right. So we know that that includes 34%. So 0.34. And we know that to the left of the mean is 50%, or 0.50. So together, it's 34. It's 0.84. So that's all of this here, 0.84. Or 84%. So it's always a good idea to begin with a sketch, to have clarity about the values that we have and what you're supposed to compute. For the next exercise, we are asked to determine something about cereal boxes. A certain dry cereal is packaged in 12-ounce boxes. The machine that fills boxes is set to fill on average a box contains 12.4 ounces. The machine-filled boxes have content weight that can be closely approximated by a normal curve. What is the probability that a randomly selected box will be underweight in other words, weigh less than 12 ounces if the standard deviation is as follows: 0.5 ounces, 0.4 ounces, 0.3 ounces, and 0.2 ounces. So we begin with a little normal curve with a mean of 12.4, because we're told the average is 12.4 ounces, these ounces. And so we ask, what's the probability that a randomly selected box will be underweight, net weight less than 12 ounces, if the standard deviation is as follows. So we have our normal curve, 12.4 and 12 ounces being here. And then our z-score would be x minus x bar divided by s. And so it's 12 minus 12.4 divided by s, or 0.4 divided by s. So for 41, number 41, s is equal to 0.5. So then the z-score is equal to minus 0.4 divided by 0.5. And that's equal to minus 0.8. And the area corresponding to z equals 0.8, or minus 0.8 is equal to 0.288. So the area is equal to 0.288. That's, in other words, we're looking for the area here. We know the half area is 0.5, so to find this area, we need to subtract this area to be found from 0.5. So 0.5 minus 0.288 is equal to 0.212. So that's the probability of finding a box that weighs less than 12 ounces when the standard deviation is 0.5 ounces. Again, we use the same formula for all the other standard deviations, so only the denominator changes. So this was for 41 rather. If we go to 42, then z is equal to minus 0.4 divided by s, or 0.4, or negative 1. And the area corresponding to z-score of minus 1, the area is equal to 0.341. 0.341. So then the area we're looking for, the probability, would be 0.5 minus 0.341, or equal to 1.59, 0.159 rather. So for 0.5 ounces, the probability was 0.212. For 0.4 ounces, it was 0.159. And then for 0.3 ounces, again, we use the same formula for 43. Z is equal to minus 0.4 divided by a standard deviation, in this case 0.3, which is minus 1.33. And the area corresponding to that is equal to 0.408. Again, let's look in the tables, and the area corresponding to the z-score of minus 1.33 is, or 1.33 is 0.48. Is 1.33. Here's the 1.33, and the corresponding area is 0.408. So then 0.5 minus 0.408 is equal to 0.092. So it would be 0.092. And then for the last one, when the standard deviation is 0.2 ounces, so for 44, we have z equals minus 0.4 divided by 0.2. That's equal to minus 2. And the area corresponding to a z-score of minus 2 is equal to 0.477. 0.477. Again, we can just look at the table. The z-score of minus 2 or 2 is 0.477 right here. So then we subtract that from 0.5 minus 0.477. So it's equal to 0.023. So that would be the probability. For the last exercise, we have the question: the time taken by workers to assemble a certain kind of cell phone are normally distributed with a mean of 18.5 minutes and a standard deviation of 3.8 minutes. Find the probability that one such phone will require less than 12.8 minutes to assemble. Okay, so what do? Well, we begin with a graph, the normal distribution here. And the normal distribution might look like this. So we have the mean at 18.5. And so then the question is, what's the probability of finding a phone that requires less than 12.8 minutes? 12.8. So here the time is measured in minutes. So the first thing we do is we find the z-score for 12.8 minutes. So then, in other words, z is equal to 12.8 minus 18.5 divided by the standard deviation of 3.8, and that is minus 1.5. That's the z-score here. So then when we look up the z-score for minus 1.5, the corresponding area, 1.5, the z-score is 0.433. That's 0.433. So the corresponding area is 0.433. So now we need to subtract it from the half area because all of this is half, and so to find the little tail area, so it's 0.500 minus 0.433, and that's equal to 0.067. So that's the probability that one such phone will require less than 12.8 minutes to assemble. Again, the idea always is to begin with the distribution, indicate the values that you have, and think about what the question means in the context of the graph. And this concludes the section. section 12.5.